Welcome to Animal Supersenses, the show that plugs you in to how animals experience the world, often with sharper and more evolved senses than the one species who likes to think of itself as the top of the food chain. That would be us, of course. While all life began in the oceans, human beings now rely on technology to navigate the seven seas, left to our own devices. We're like the proverbial fish out of water, only the other way around. Once underwater, with light diminished, our vision becomes blurred. Our hearing becomes muffled and distorted. And our sense of smell is rendered completely useless. Now compare that, for example, to that renowned predator, the great white shark. This elegant killing machine is perfectly attuned to every sight, sound, scent, chemical, and electrical signal of its marine environment. We'll pay a slightly nervous visit to the great white a little later in the episode. But first, listening carefully? Because the sense of hearing enters a whole nother dimension when applied to creatures of the deep. Hearing is critical for animals such as the sperm or humpback whale. For one thing, light fractures and weakens underwater, so vision becomes a less important tool for survival. Sound, however, travels further in the water than in the air. So for whales, it's critically important as a way of communicating. Most famously, as in the song of the humpback whale. Humpback whales are members of the cetacean family, which includes whales, dolphins, and porpoises, all of which have well-developed senses of hearing. In the case of this humpback whale, its outer ear is a very small opening that closes once underwater. Instead, it picks up on waterborne vibrations through bones in its head. Good vibrations that ultimately reach its middle and inner ears. Fascinatingly, the ancestors of the whale actually walked on land. Pakistanidae, or Pakistani whales, lived on the shores of the Indian subcontinent and began to diversify, making for the water some 53 million years ago, give or take. More about them and their ancestors later in the show. Meanwhile, to be a little bit more specific about what hearing is, it's the ability to sense sonic vibrations. Sound and what is known as vibrational stimuli, they pretty much amount to the same thing underwater. The scene now is the Coral Triangle. This is the area of tropical marine waters around Malaysia, the Philippines, Indonesia, and East Timor. A tropical paradise in many regards, sometimes known as the Amazon of the seas. but one that the World Wildlife Foundation is keeping a close eye on to ensure human activity doesn't spoil this particular paradise too. Among the countless species that call the Coral Triangle home, you'll find plenty of cephalopods. Plenty of what? Cephalopods, like cuttlefish and this octopus, are invertebrate, spineless mollusks with generally large heads and symmetrical bodies. For over a century, there's been a debate as to whether these creatures are capable of hearing. But the consensus seems now to be that they can, either by something called the statocyst organ, a fluid-filled sac lined with sensory hairs that also helps them to maintain balance, or they can hear via lateral lines, similar to that found in fish, visible lines on the fish's body comprised of sense organs which detect pressures and vibrations. Now, of course, there are more fish than you can shake a million fish sticks at in the Coral Triangle, and chances are they'd hear you when you shook those sticks at them. Because as any goldfish owner can tell you, at any kind of threatening sound, a fish will curl into a tight C shape and head in the opposite direction. So whether in a goldfish bowl or the Coral Triangle, we know that fish can hear, but believe it or not, scientists are somewhat divided as to how. Here are the two main theories. The bodies of fish have about the same density as water, which means that sound passes through their bodies. But fish have bones in their inner ear, which are called otoliths. These bones are denser than both the water and the fish's body. This means these bones move at a slower pace than the rest of the fish's body, and also the speed of the sound waves. The upshot of this is that the difference in speed between the otolith bones and the rest of the fish's body ruffles the hairy sensor cells located in its inner ear. This differential movement is interrupted by the brain as sound. Then there are the lateral lines we mentioned before. These are essentially a set of tubes located just under the fish's, or in this case, the shark's body. Water enters these tubes through the pores of the skin. The tubes are lined with hair cells, which are connected in turn to sensory nerves. When anything gets close to a shark, the water running through the lateral lines moves to and fro. This stimulates the sensory cells, which alerts the animal to whatever prey or predators may be in the vicinity. When we talk about animal supersenses, perhaps no animal fits the bill more than the shark. In the popular imagination, we imagine them, like this blacktip shark, moving stealthily through the water and then seizing their prey without mercy, relentless and unstoppable. And that's about the size of it. Their senses are also supremely well adjusted to make them effective underwater predators. For one thing, they have a particularly acute sense of smell. Unlike, for example, human beings, sharks have separate and distinct openings for breathing and for smelling. The gills on the side of their heads are for breathing only and serve to capture oxygen in the water. Meanwhile, two nostrils to the front of their heads pull water into a nasal chamber, specifically dedicated to detecting smells. Perhaps one reason a shark's nose works so well is because it doesn't have to do anything else. Breathing is accomplished with their gills, and a shark's sense of smell is not in any way connected to its mouth. But a shark's sensory arsenal doesn't end there. Sharks come with a unique sense organ as standard equipment, something called the ampullae of Lorenzini. They were first described back in the 17th century by one Stefano Lorenzini. They consist of small clusters of electrically sensitive receptor cells found just under the skin. These are connected to the water by pores on the shark's snout and head. What the ampullae of Lorenzini do for the shark is to outfit it with electroreception. In a nutshell, electroreception means the shark can sense the bioelectric fields generated by other animals and use it to locate them. And hey, you'd expect the ultimate predator to know where its next meal is coming from, right? Black-tip sharks like these share the waters of the Coral Triangle with a cetacean known for its hearty appetite, the sperm whale. And also with the sperm whale's distant cousin, the dolphin, a marine mammal who is no slouch in the appetite department either. They may be enthusiastic eaters, but they don't exactly enjoy their food in any way we might understand. You see, just about all vertebrates enjoy 5 primary tastes: sweet, salty, sour, bitter, and umami, except that is for cetaceans such as dolphins and whales. New research has revealed at some point in their evolutionary journey, they lost the ability to perceive anything but salt. Scientists believe this took place between 53 million years ago, at the point when whale ancestors, Pachycetidae, took to the seas, and 36 million years ago, when they split into 2 groups, toothed and baleen whales. Then again, if you swallow your food instead of chewing it, perhaps not having a sense of taste isn't such a great loss. What about underwater vision? All you need to do is hold your head underwater for a few seconds, and you'll see that our eyes are not adapted for vision underwater. No, they've evolved for viewing in air. Everything is a blur underwater, right? That's because light rays bend when they travel from one medium to another, from air to water. Water refracts light at roughly the same degree as the cornea of the human eye, which effectively eliminates our ability to focus. Fish eyes are more spherical in shape, allowing them to focus under the waves. In many cases, they're also sensitive to a larger range of the color spectrum, including ultraviolet light. As light passes through deeper and deeper waters, more color is absorbed and diluted. The water filters out the color red at first, then yellow, then green, and then violet. The color blue is the last to go. And yet, as recent studies show, ultraviolet light penetrates far deeper into the water than used to be thought. Could this be the reason why so many fish are so very colorful? That while their colors might, to the human eye, be muted by the ocean depths, to a fish with ultraviolet sight, these creatures still stand out as bright and beautiful. The answer appears to be yes. In some cases, many coral reef fish, for example, are brightly hued, coming in a dazzling array of colors. The harlequin tuskfish, mandarin fish, coral trout, regal angelfish, and stoplight parrotfish all spring to mind. Scientists believe that some fish use their brightly colored skins to attract a mate. But, as with so much in nature, it's more complicated than that. For color is also employed by some fish as a warning system, a warning to back off and stay away. Lionfish, for example, are thought to utilize their brightly colored bodies to communicate to other animals that it's best to stay away from them, and more especially, their highly venomous spines. Then again, there are instances when fish like to blend in with their surroundings. Literally, it's called cryptic coloring, and it enables some species of fish to camouflage themselves. A predator, like the great white shark, might seem like the last customer who would need to hide itself away. But the great white, along with many other open sea fish, uses counter shading to camouflage itself on a regular basis. But one of the strangest and most effective underwater senses is known as echolocation. This is very much what it sounds like in a way, being able to locate something because of its echo. It's also known as sonar, which humans have studied and replicated, for example, for use in submarines and naval warfare. This is a system for detecting objects underwater by emitting a sound pulse. And then being able to detect and measure it upon its return to find out where something is, its size, and so on. Call it seeing with sound, because in effect, that's what it is. Dolphins use echolocation all the time. Like all toothed whales, dolphins have specialized fat located in their jaws which convey sound waves from the ocean to their ears. They use echolocation to crater feed, meaning to find prey underneath the sand, because unlike other senses, echolocation can penetrate or see through solid matter. It's a primary sense for dolphins and other species of toothed whales. That's right, a dolphin is also a type of whale, a type of toothed whale, to be precise. Other varieties of toothed whales include sperm whales, killer whales, and beaked whales. All of these creatures use sonar, or echolocation, to guide them through the oceans, to communicate, and to detect prey. As you'll recall, the distant, 50 million years plus distant ancestors of whales were actually land-dwelling mammals, who probably saw things quite well in the open air. Echolocation helped them adapt to life underwater. Navigating the open ocean, with its shifty currents and expansive water, for most animals is no easy feat. But sea turtles have to face up to the challenge. There are 7 species of sea turtles found in the oceans all around the world. They spend their first few years floating in the open sea, where they feast on jellyfish and other creatures. But at some point, they need to find their way to the beach to breed. And it's not just any beach. They return to the one they were born on. How they actually do this is still being debated, but it's thought they may use the Earth's magnetic field as a cue, and perhaps their sense of smell plays a role as well. On this stretch of South American shoreline, an olive ridley turtle clambers slowly up the beach. This female adult is about to lay a clutch of eggs. Over 100 eggs can be deposited in a nest at any one time. Once the eggs are buried, the adult returns to the water. After incubating for over 45 days, hatchlings emerge to begin a perilous journey. They race to the water's edge, but vultures with a taste for turtle are patrolling. And even when they reach the sea, it's still not safe. Few hatchlings make it to the feeding grounds in the open ocean. It could be why the olive ridleys have a remarkable nesting strategy. In a spectacular mass nesting get-together known as an arribada, thousands of females come ashore simultaneously to lay eggs. How the females know the time is right is unknown. They may release a scent that cues the start, but with no conclusive answer, the arribada continues to be one of nature's great secrets. On Animal Super Senses, we've taken you from the surface to the depths of the seven seas to seek out the treasures below. From the tiny, colorful fish of the coral reef to the mighty sperm whale, we've explored how these creatures hear the vast beauty of the ocean world. It could make you wonder why our ancestors ever came out of the water in the first place. Just be sure we'll come to our senses again next time on Animal Super Senses.